For the last couple of years, really, when we think about artificial intelligence, we usually picture this very specific type of interaction.
Right, sitting at a keyboard.
Exactly. You're sitting at your computer, you're staring at a web browser, and you are just typing into this little text box. It's quiet, it's entirely text-based. It feels, I don't know, safely contained right there behind a screen.
Yeah, it's a very asynchronous typing-driven
Yeah.
paradigm. You send a message, you sit there and wait for the machine to, quote-unquote, think, and then it types a response back to you.
Mm-hmm.
I mean, it's powerful, sure, but it's very deliberate and honestly a bit isolated.
It really is. But what happens when the AI jumps out of that little text box, walks right past your web browser, and just starts directly dialing your cell phone?
Yeah, it changes everything.
It totally does. And that is exactly what we're getting into today. Welcome to the deep dive. We've got this fascinating stack of architecture documents and visual guides on the table, and our mission today is to figure out exactly how developers are taking these massive, complex AI brains and hooking them directly into the global telephone network.
It's wild stuff. We're taking you entirely behind the scenes of how this actually works.
Okay, let's unpack this. Looking at our materials, there is a section that sets the stage perfectly, and it's on the first page under the heading. The era of voice AI, bridging cloud intelligence and mobile telephony.
That title really captures the monumental shift we're seeing right now. I mean, the executive summary in this first section lays it out so clearly. We are fundamentally transitioning from those text-based chatbots you just mentioned to real-time dynamic voice execution.
Right, voice is the new interface.
Exactly. The core goal here is to route cloud intelligence directly to a standard 10-digit mobile phone number. And, if you look at the exact focus of this page, it's all about framing why this matters. Because it unlocks absolute mass accessibility.
Oh, because you don't need to, download a specialized app or own some $1,000 smartphone to access the AI.
Exactly.
You just need a phone that can make a basic standard phone call.
Precisely. Whether it's a landline in a rural office or an old flip phone, it works. It's about seamlessly crossing the bridge between modern large language models, the LLMs that power the AI, and the legacy telecommunication networks that have just spanned the globe for decades.
Which, sounds amazing in theory. You just plug the super smart AI into the phone line, right? Simple.
If only it were that simple.
Right, because historically, building that bridge has been an absolute nightmare. And that actually brings us to a really illuminating part of our visual guides. Let's look at the exact heading of the second page, the problem. The complexity of telecom-AI integration.
It really is a classic clash of generations. You are trying to force modern AI infrastructure, which operates at literally the speed of light, to talk to telecommunications infrastructure that, in many ways, hasn't fundamentally changed its underlying routing logic since the days of copper wires and physical switchboards.
Yeah, our documents highlight this as a protocol mismatch. And reading through how these two systems try to talk to each other, the best analogy I could think of is imagine trying to speak fluent, rapid-fire French to someone who only communicates in Morse code.
Yeah, this is a great way to put it.
Right, because on the modern AI stack side, you have web APIs and WebSockets. And WebSockets are lightning fast. They keep a digital connection open and just stream data back and forth continuously with sub-second requirements. But then on the legacy telecom side, carriers demand these really strict SIP Handshakes session initiation protocol.
Yes, SIP is incredibly rigid. It is a step-by-step, highly methodical process designed to ensure a call doesn't drop between cell towers. I mean, it was never designed to handle the continuous fluid data stream of a conversational AI.
So they just don't speak the same language.
Not at all. And that protocol mismatch is exactly what causes the biggest issue highlighted on page 2, which is severe latency bottlenecks.
Let's talk about that latency because the traditional way of building these voice agents sounds completely exhausting.
Oh, it was brutal. In the past, developers had to essentially chain together separate, isolated services. So first, the audio comes in from the phone, and it hits a speech-to-text service, or STT, just to transcribe what the caller actually said.
Right, just turning sound into words.
Exactly. Then, that text file gets passed over to the LLM, so the AI can figure out an answer. Once it generates a text answer, that text gets passed to a third service, text-to-speech, or TTS, to generate the audio response. Doing that sequentially, like a bucket brigade style, introduces massive, unnatural, multi-second conversational delays.
But wait, doesn't that completely ruin the illusion of talking to a smart agent? If you're waiting 3 or 4 seconds for a reply every time you speak, what happens?
You start talking over each other.
Exactly. You say hello and wait 3 seconds, assume the call drops, say hello again, and right as you say it, the AI finally responds. It's a mess.
It entirely shatters the illusion. Human conversation relies on split-second timing, overlapping speech, and instant audible feedback. If there's a delay, the trust is broken immediately.
Oh, for sure.
And what's crazy is that to even get that laggy, frustrating experience, the document points out the massive infrastructure overhead developers were burdened with. They were literally forced to build and maintain their own custom audio transcoding servers just to translate the AI's web audio into the highly specific, compressed format the phone company needed.
Which sounds expensive.
Incredibly heavy, prone to breaking,
Yeah.
and very expensive.
So the old way is clearly broken, it's laggy, it requires a massive server farm just to process the audio, and it frustrates the caller. Thankfully, our sources don't just point out the flaws, they give us the blueprint for the modern fix.
Yeah, the new approach is brilliant.
Let's look at how they solve this. I'll read the exact heading of the third page. The solution: a unified telephony architecture.
This is where we see the real paradigm shift. Instead of chaining a bunch of disconnected third-party tools together and hoping they communicate, this unified architecture uses a single SDK, a software development kit, to orchestrate the whole thing. It replaces those messy legacy systems with 3 core synchronized pillars.
Okay, let me see if I can break those pillars down based on the architecture map here.
Go for it. Let's start with the first one.
Actually, you explain the first one. Obviously, you need the brains of the operation.
Right, so the first pillar is the intelligence. In the specific architecture outlined in our guide on page 3, they're using Google Gemini as the foundational LLM. This isn't just a basic script. This is the cognitive engine that actually understands the user's intent, parses the context of the conversation, and defines the logical response.
Okay, got it. Then you have the second pillar, which they call the Orchestrator. According to the visual guide, this uses a platform called VideoSDK alongside a lightweight local Python worker. If I'm understanding this right, this acts as your central cloud router, right?
That's right.
So it basically manages the real-time audio loops so you don't have to build those custom media servers we were just complaining about.
Exactly. It handles all the heavy lifting of the audio translation in the background. And finally, you have the third pillar, which is the bridge. Because at the end of the day, you still need to connect to the actual physical phone network.
Right, you need a real phone number.
Exactly. Here, they use a Twilio SIP Trunk. This is the service that actually provisions that 10-digit phone number and connects the end user dialing on their cell phone to your cloud setup. What's fascinating here is how these 3 pillars communicate.
Oh, so they don't use that clunky bucket brigade method anymore?
No, absolutely not. Because of that unified SDK, they use a continuous SIP and WebRTC stream. WebRTC is the technology that allows real-time audio and video streaming directly through web protocols. By binding these together, it completely eliminates those multi-second manual handoffs.
Wow.
Yeah, the audio flows like a single continuous river from the caller, through the AI brain, and back to the caller's ear.
Okay, so the architecture is fully mapped out. We've built the unified bridge, but a bridge is just infrastructure. It's empty. How does a developer actually bring this AI to life?
We have to give it a brain.
Right. How do you give it a personality so it doesn't just sound like a robotic dial-up modem reading an encyclopedia to you? Our documents tackle this head-on. Let's look at the exact heading of the 4th page. The brain, provisioning the LLM in persona.
This is a really interesting pivot on page 4 because this is where the workflow shifts from deep, complex telecom engineering to straightforward prompt engineering. The agent's actual capabilities and its overall vibe are defined by configuring that foundational LLM.
And looking at the Python configuration code provided in this section, I'm just marveling at how simple it actually is. It's literally just a few lines of plain text code. You pass it an API key to authenticate it, you give it a system prompt, and you set some basic lifecycle hooks.
And just to clarify, lifecycle hooks are basically automated instructions for when a call starts and ends.
Right, like an on-connect greeting where you just type, "I am your real-time assistant, how can I help?" and an on-disconnect hook that says goodbye.
Yeah.
That is practically it.
It really is. The document gives us an AI agent dossier to show how this manifests in the real world. They named the agent My Telephony agent. The base model is Google Gemini. Its core directive, which is fed into that system prompt you mentioned, is simply to be concise, friendly, and answer phone calls.
Simple enough.
And finally, it's assigned a human-like natural synthesis voice profile.
But let me push back on that for a second because this sounds way too easy. We just type the words "be friendly" into a configuration file, and suddenly this machine knows how to handle a complex, unpredictable phone call with a frustrated human being.
I know, it seems like magic, right? But it's really just the power of foundational large language models. Because a model like Gemini has been trained on vast amounts of human dialogue across the internet and literature.
So it already knows what being friendly sounds like.
Exactly. It intrinsically understands the nuances of what a friendly tone looks like. It understands pacing, and it understands how to de-escalate or answer questions naturally.
Okay, so you aren't teaching it from scratch.
Not at all. The strict system instructions you provide act as guardrails. You aren't teaching it how to speak. You are constraining its vast, generalized knowledge into a specific, highly focused persona. You're effectively telling it, out of all the things you could possibly be right now, ignore everything else and just be a concise, helpful phone operator.
That makes a lot of sense. You're carving the statue out of a marble block. So the brain has its personality, it has its guardrails. But a brain sitting in a jar on a desk doesn't do much.
No, it doesn't.
It needs a heartbeat. It needs to be turned on. How does it actually run? This brings us to a really empowering part of the guide. I'll read the exact heading of the 5th page with a lot of enthusiasm because this is cool.
Yeah.
The engine. Deploying the Python worker.
This section walks us through the lightweight local setup, and lightweight is the absolute key word here on page 5. We have to remember we aren't spinning up massive server farms or specialized hardware anymore.
Right.
A developer can run this entire telecom node on their own local machine, just running a background process to register and maintain the active state of the agent.
The guide breaks it down conceptually into 4 ridiculously simple steps. Step 1 is setup-im, which really just means explicitly telling your computer which code libraries you need to install so everything runs smoothly.
Yep.
Step 2 is load keys, which is how you securely authenticate your VideoSDK and Gemini accounts. Step 3 is register ID, which tells the cloud, hey, I am initializing a worker job, and its unique name is my Telephony agent. And finally, step 4 is poll for jobs, which keeps the connection alive and active.
And let's explain polling for jobs, because it's a fundamental concept here. It just means your local script is standing by, constantly tapping the server on the shoulder. It's like a taxi driver idling at a cab stand, constantly checking the dispatch radio, asking, got a fare for me? Do you have a phone call for me?
Just waiting.
Yeah, you're just waiting in a state of readiness for an inbound or outbound trigger.
Here's where it gets really interesting to me. To start this entire AI telecommunications node, you literally just open your computer's standard terminal window, run a couple of basic installation commands to grab those libraries we mentioned, and then execute your main Python file. Just type python main.py.
That's it.
Instantly, the system authenticates your tokens, flashes a success message that the agent is registered, and prints out, worker is running, listening for jobs. Suddenly, your standard laptop sitting on your kitchen table is actively plugged into the telecom grid, waiting to process human speech.
It drastically democratizes telecom development. It takes it out of the hands of specialized engineers and gives it to anyone with basic coding knowledge.
It's incredible.
But to your point about the telecom grid, running a Python script locally is impressive, but a phone agent needs a phone number.
Right, because I've checked, and my laptop definitely does not have a phone jack.
I would hope not.
If I dial a standard 10-digit number from my cell phone, how on earth does that signal find its way to a Python script running on my kitchen table? That brings us to the architecture detailed on the next page. Here is the exact heading of the 6th page. The network, establishing the SIP trunk.
This page focuses on where the virtual world meets the physical world. To translate cloud-based data into standardized mobile carrier signals, you need something called an elastic SIP trunk.
Okay, and looking at the diagram here, we've got 2 main circles representing this. On the left side, we have the telecom provider, in this case, the Twilio API. They're the ones actually providing that physical provision 10-digit phone number.
Right.
They are plugged into the PSTN, the public switch telephone network, which is the global grid of cell towers and landlines. They receive the signal from the cell tower and translate it into digital data. Then, on the right side of the diagram, we have the Cloud Orchestrator Video SDK.
Correct.
They provide a unique routing URL, taking your cloud data and translating it back into carrier signals.
And right in the middle of those 2 circles is a giant padlock icon. This represents the secure handshake.
Okay.
You have to establish that elastic SIP trunk using strict administrative credentials. This is a vital security step. It ensures that only authorized cloud applications can push calls to the mobile network.
Because otherwise, someone could just hijack the line.
Exactly. Without that secure handshake, malicious actors could spoof your number or worse, hijack the AI's audio stream entirely. The handshake locks the connection so that Twilio and VideoSDK trust each other completely and exclusively.
Okay, so the plumbing is fully connected and it is secure. You have the brain configured, you have the Python engine humming along on your desk, and you have the secure phone line routing through the telecom provider.
You're all set up.
But now you need a way to tell the whole system when to actually pick up the phone or make an outbound call. We need a control room, and that is exactly what we find outlined next. The exact heading of the 7th page is Orchestration, Gateways, and Routing Rules.
This represents the cloud dashboard. It acts as the command center for the entire operation. This is where you map the physical telecom assets to the specific AI agent processes running locally on your machine.
The visual they provide on page 7 makes it so clear. On one side of the dashboard, you have your physical asset, the telecom gateway. Let's say you went and purchased the number +1 555 019 8472.
Right.
On the other side, you have your local Python worker process, which we uniquely identified earlier as my telephony agent. Sitting right in between them is the routing rule engine.
And the real value highlighted in this section is the no-code UI, the user interface. In the past, connecting that physical phone number to that cloud agent ID required writing raw, complex telecom routing code.
Sounds awful.
It was. You had to manually handle failure states, manage deep SIP headers, and write fallback logic. Here, the dashboard just uses simple visual toggles.
It's literally like an old-school switchboard operator just patching the cables through for you. You just flip the outbound trigger switch to on. The cloud dashboard automatically routes the signals from that 555 number directly to your Python script. It completely abstracts away all of that underlying telecom complexity.
It does. It handles all the messy routing logic invisibly.
So the setup is finally complete. All the green lights are on. It's time to actually make a call. What actually happens in the split second after the person on the cell phone says hello? Our guides break this down beautifully. The exact heading of the 8th page is Synthesis, the real-time voice loop.
This is the moment of truth for the entire architecture. Page 8 outlines a 4-step millisecond loop that happens completely seamlessly. Step 1. User speaks. The physical mobile device captures the human voice.
Okay, step 1 is easy.
Step 2. Audio routed. That secure SIP trunk we built transmits that audio to the cloud where it is instantly transcribed to text.
Then we hit step 3, brain processes. The Gemini LLM parses the user's intent from that text and immediately generates a text response based on its persona guardrails.
Exactly.
And finally, step 4, voice response. That text response is synthesized into human-like audio and routed straight back down the pipeline to the speaker's cell phone earpiece. And this entire loop, all 4 of those complex steps, happens in a fraction of a second.
We connect this to the bigger picture. That sub-second latency we keep mentioning is not just a neat technical flex. It is the absolute, non-negotiable requirement for making an AI agent capable of executing real-world tasks naturally.
Because humans are impatient.
Very. Think about it. If the agent is going to successfully book a complex hair appointment for you or handle a frustrating customer service return, it has to react as fast as a human. This integrated stack, streaming the audio continuously via WebRTC rather than stopping to process it chunk by chunk, is what makes that seamless natural loop possible.
So we've walked through how this works, and it is undeniably slick. But I have to ask the ultimate question on behalf of our listeners, the skeptical question. You could theoretically build this yourself from scratch, right?
Oh, absolutely.
Utilizing all those individual APIs manually. So why use this specific integrated SDK stack? The documentation actually addresses this head-on. Let's read the exact heading of the 9th page. Comparative analysis. AI native vs. traditional integration.
It really comes down to a classic build versus buy scenario. But the metrics here on page 9 heavily favor the integrated SDK approach.
Yeah.
The table in this section contrasts the traditional custom build against SDK agent integration.
Okay, let's break it down.
Let's just look at the architecture setup phase. A traditional build requires deep WebRTC and SIP protocol expertise. You literally need to hire dedicated telecom engineers. The SDK integration. It requires basic Python execution and simple API writing.
And we already covered the latency difference. Manual chaining causes severe lag and talking over each other, while the SDK ensures continuous parallel streaming for a natural conversational flow.
Right.
But the row in this table that really jumps out to me is the infrastructure comparison. The old way demands deploying, maintaining, and scaling your own custom media servers. The new way relies entirely on a serverless cloud backend that you don't even have to look at.
And that leads directly to the most important metric for any business or developer: time to market.
Exactly. The comparative analysis states that traditional builds take weeks of agonizing protocol debugging just to get a basic hello world working over a phone line.
It's painful.
But utilizing this unified architecture allows a developer to deploy a highly intelligent AI agent to a mobile device in a single afternoon.
Right.
You go from weeks of banging your head against legacy SIP protocols to having a functional, intelligent voice agent working before you even clock out for the day. That is a massive leap in human productivity.
It's a complete paradigm shift.
Hmm.
But an afternoon prototype running on your kitchen laptop is really just the beginning of the journey.
True.
What happens when your listener wants to release this agent to thousands of their customers simultaneously?
Right.
You obviously can't run a global call center off a Python script on your kitchen table. Your laptop would literally melt.
Which brings us to the final piece of the puzzle in our guides. We find the roadmap for scaling up under the exact heading of the final page, page 10. Next steps: scaling your voice agent.
This page outlines what they call the staircase to production. It provides a really clear, logical roadmap for taking that afternoon project and making it fully enterprise grade.
The first step on the staircase is exactly what we just built today. Local outbound. A functional prototype running locally on your machine just to prove the concept works.
Yeah, starting small.
But then you step up to the middle tier, which they call inbound and DB integration.
Right. Once you're comfortable with the outbound calls, you reverse the routing rules in that cloud dashboard to support 24/7 inbound automated support so people can call you.
Which is huge.
And crucially, this is where you connect your Python worker to internal databases and APIs for live data fetching. So instead of just making polite small talk, your agent can actually check inventory databases in real time, pull up a customer's order history, and execute real, tangible actions.
It goes from being a conversationalist to being an actual worker.
Exactly.
And finally, you step up to the top of the staircase, cloud-hosted 24/7 uptime. You take that Python worker out of your basement, so to speak, and you migrate it from your local environment to a stable, robust cloud provider like AWS or Render.
But there's a vital warning here for developers making that jump. The document includes a critical requirement box on this exact transition.
Yes, I'm looking at it. It says developers must ensure SDK plugins are strictly pinned in their requirements file. Why is that so crucial?
It is incredibly important because of how cloud environments work. When you move from your laptop to a cloud server, if you haven't pinned your dependencies, meaning explicitly stating, for example, I need exactly version 0.0.67 of this library, the cloud server might grab a newer, slightly different version of the code when it boots up.
Oh, I see.
That can cause catastrophic runtime mismatches, where your agent just suddenly stops understanding the network signals during scaling operations. It's a tiny administrative detail that can literally save you hours of pulling your hair out over mysterious downtime.
Pin your dependencies, folks. Always good advice when scaling. So what does this all mean? We started this deep dive looking at a massive, frustrating gap between modern AI, which moves at the speed of light, and legacy telecom networks that demand rigid, old-school handshakes.
A huge gap.
We've seen how a unified SDK acts as the ultimate translator. It allows you to spin up a highly intelligent conversational AI brain, configure its personality with just a few natural language prompts, and run it as a lightweight Python worker polling for jobs.
It's elegant.
In a single afternoon, you can securely route that intelligence straight to a 10-digit phone number, bypassing weeks of protocol debugging.
It completely takes the friction out of the system. It allows developers to focus on what actually matters, the conversational experience and the utility of the AI, rather than acting as a digital plumber trying to force telecom signals through a pipe.
And for you listening right now, I want you to really think about how this changes your own workflow or your business. The barrier to entry for building a voice-native AI agent has essentially dropped to zero. If you know basic Python, you can now build a telephone operator, a customer service rep, or a personal assistant that lives on the global phone network and can interact with anyone, anywhere.
Which raises an important question to leave you with. We've seen the architecture. We know the sub-second millisecond loop works flawlessly over a standard phone line. So the next time you call a business and a friendly, concise voice answers the phone, perfectly understands your complicated problem, and instantly accesses the database to fix it, well,
Yeah.
How long until you don't even realize you aren't talking to a human at all, but rather a lightweight Python worker polling for jobs in the cloud?
And honestly, if your problem gets solved in record time with zero hold music, does it even matter?
That is something to think about the next time your phone rings. Thanks for joining us for this deep dive into the architecture of voice AI. We'll see you next time.
Take care.